SwayamPrabha. Digital India. Educated India.
So, now we are on lecture 25, which is the last lecture of this module on introduction to auditorium design. Here, after knowing all the concepts which has been discussed in the earlier 4 lectures, I will try to show you the applications in some very good halls which are quite renowned, and these are not made by individuals. Yes, the design architect may be one, but acoustical experts have designed the interior, and even then after making it, a number of trials, number of changes are still being done in some of the halls. So, you will see how really the principles have been applied, and yes, whether they have made a good impact or bad impact, you can see it by yourself or understand. And fortunately, many of you may be fortunately visiting all these halls in later part of your life, and yes, that time you may remember or recall this particular course. So, this is the famous Symphony Hall Boston, which was the interior was done by Clement Sabine. So, this was in 1900, and here you barely see lot of details. This was a shoebox hall, and the reverberation time achieved was targeted was 1.8 seconds, capacity is 2625, and height, width, length all are written over there. The flooring is all of wood, and the balconies were not actually the way we had planned or shown. So, that has come up with time. You can see the balconies here on the sides. You can see the balconies here. So, these were very narrow balconies on the side to avoid any kind of trapping of sound or muffling or sound. So, sound cannot get trapped inside it. Keeping that in mind, those were made very small projections at the sides. You can see a rich coffered ceiling on top. So, it was spanning this 22.9 meters, that is around 23 meters, and obviously the single beams would have been very heavy. So, these coffered beams were planned, in which the side of the or the edges of the beam allowed in diffusing sound, and the flat slab areas actually helped in reflected sound. So, these particular segmented areas helped in reflecting sound into the audience, and these projected soft beams all helped in diffusing sound into the hall. There were lots of statues at different positions. You can see one very faint over here. So, there were statues filled niches which also helped in diffused sound into the hall. So, these are studied, these were made, and these were checked. The seats were all made of, had leather upholsteries. So, these were all experimented and put in, and it achieved the RT of 1.8, and this is one of the famous halls which was acoustically designed by Clement Sabine. We come to the next hall, the Avery Fisher Hall, which has a capacity of 2738 and made in 1962, where you see here at the ends you see a lot of convex surfaces. These are all wooden surfaces to reflect sound. These are maple wood convex surfaces, but these were not initially there. These are all additions to help sound to be reflected towards the people, because the hall was not receiving much of first reflections from the side walls. This is also a shoebox shape, but the side walls were far away. So, the central part or the central part of the sitting was not getting reflected sound from the walls, and the central audience were devoid of sound. Same thing happened from the ceiling side. The reflected path from the ceiling were too long. So, these clouds, these shaped surfaces on the ceiling were too high to reinforce the source sound and help in early reflections adequately. So, lot of things were with time were added, of which these maple wood convex surfaces were one, and in this hall, because there was no other shape than straight flat things, the bass was weak, that is the low frequency was lost. In that case, it could not achieve better sound quality for that is the warmth was lacking in this particular hall. But yes, later lot of changes have been made and a lot of improvement has been done to achieve a better quality. We move to the next hall, which you all know, Sydney Opera House by John Ardson. It has multiple number of halls. It has more than apart from this, there are many other halls in this, but this hall is of particular importance. This site is a UNESCO World Heritage Site. So, inside this, the sound was really criticized. The quality of sound inside this particular hall was really criticized, but a lot of improvement has been done, and yes, till date it is being upgraded for acoustical quality. Here you can see the view from the view towards the stage. You can see on the top here there are a number of clouds which are convex shape and allowing sound getting reflected back to the stage, so that the players here can get the sound from the top and get an ensemble sound. Here if you observe, it is a shell structure. You can see this sawtoothed profile which helps in diffused sound inside towards the audience. This is a view from the stage side towards the sitting. These acrylic rings can be adjusted height wise to achieve a better sound quality or better ensemblement for the players over here, the orchestra players over here, and also to send the sound in the towards the audience. These clouds, acrylic clouds, were later changed put with infills. Rectangular reflectors were put in, various experiments were done, height was adjusted, and things are still being tried out and to achieve a better sound quality. All the seats over here are upholstered in wool. We see a further detailed improvised hall. These are taken from a paper which has been referred at the end. This is the acrylic cloud, and these are the reflected ceilings on the stage which has been added. You see here on the sides, which is the detailed out here, you can see in the stage area a lot of reflectors has been added to strengthen the first reflection. So, you can see MDF reflective boards, which was a very cheap solution to cover up the sawtoothed facade in nearby the stage and the front of the hall. So, these reflectors were added to improve the acoustical quality inside this hall. So, a lot of studies has been done. You can go through the internet and you can actually download papers if it is possible. Otherwise, to know this much is enough to see that within this hall, even the first reflections, these MDF boards have been added as an addition as a later stage of time. The capacity of this, you can see here, the capacity of this hall is 2679. Coming to the next hall, the Mayor Symphony Hall, Boston. Here what you see, those hanging balconies, not hanging, these are segmented balconies where sound could flow through these gaps. So, it is, some are at a inside, some are set in, some are projected out. So, sound could move in a different way which the architect has tried to achieve. You can see the convex wall surface here. So, this has been segmented and it is a wavy kind of pattern which is allowing sound to be reflected in a or diffused inside the entire hall. And you can see the stage here, there is no surround sitting. So, this is the audience over here and this is the stage, the performers working, and you can see the reflectors placed over here. So, that these performers, what this person is playing, the person over here can, the artist from here can listening what is going on there. So, this reflecting back of sound to each other within the stage helps them to perform in totality, in an integrated fashion, which is very, very important. At the same time, these are also reflecting sound towards the audience. You can see the similar kind of profile what we had seen in our Kalidas auditorium when we had discussed the stage area and the profiles. The capacity of this is 2443. So, these are all under very big sizes. This was made in 1982. Now, coming to the Verizon Hall in the Kimmel Center, which is of this century, that is 2001. Now, as I have not touched upon noise and vibration part, which will be taken up by Professor Bhattacharya, here I would like to mention that the entire hall was set over 225 rubber isolation pads to cut down the vibration or the extraneous noise from the Broadway street just beside it. The shape of this particular hall is like a violin or a cello, and if you see, the balconies are all around. It has 3 tiers of balcony and the stage is here and some sittings around, as you can see in this picture. So, all these surfaces you can see here are wavy. So, they are formed with such wavy surfaces, as you can see, this is the larger part of the audience. You can see pictures in the internet, but only this was the free picture available. So, you can see a lot of curvatures, within which again these are having curved profile. So, these are all to diffuse sound into, and this is the audience. Now, this hall, what did it have further? These had adjustable acoustical features like retractable curtains to control the RT. It had operable doors on the sides, so that they could open some doors to allow some sound to go out and achieve a different reverberation time. So, these kind of new innovations were really added in this particular hall with a capacity of 2500 to achieve a better acoustical quality. Large canopy above the stage was placed, as you have seen in the earlier, to get that could be raised or lowered depending on what kind of performance is happening, which is now tried out in Sydney Opera House. Those acrylic donut kind of shapes, clouds, which were in Sydney Opera House, are now being changed with this kind of adjustable reflector to create that ensemble quality. Now we come to the Walt Disney Hall, which is of 2003. This is like a vineyard. The plan, if you see, you will see it is kind of vineyard with, here you can see all the seatings rows are concave curves, whereas all the wall profiles, all these profiles are convex towards the stage, and this creates a drama. All surfaces reflected sound forming a transparent mesh. It is an illusion. The ceiling is made of convex surfaces, the seatings are made of concave surfaces. So, sound actually, it is a network of sound moving, a transparent network of sound moving inside, giving it a elusive feeling. It also has, similar to the Verizon Hall, it also has 500 doors, of which 200 are acoustical doors. You see the capacity here is 2265 and the reverberation time is 2.2 seconds. You can see the entire lining is of wood, which is Douglas fir, and the flooring is of oak wood. This is a very recent hall with a very small capacity, 842, made in 2013, where you can see on the sides there are a number of convex towards the stage wall surfaces, and the ceiling over is also a convex surface. So, the ceiling looks like a is very circular, and on top of it, where these all goes and merges, the ceiling is held over there. So, it is how the architect has designed it, but following, if you think properly, if you go to the earlier lectures, you will see all the principles, the same principles are being adopted in all these halls to achieve a good sound quality. And So, we had started with the acoustical requirements of a good auditorium with adequate loudness, diffuse sound level, optimum reverberation, free from defects and isolation from noise and vibration. The isolation from noise and vibration has not been touched upon here much, but we have tried to cover all these particular requirements which we started with. And to conclude, if you want a good quality, acoustical quality, loudness, spatial impression, intimacy, early decay time, clarity, warmth and brilliance, background noise, volume, sight line, view, sitting plan, if you account for all these things together, you will surely achieve a good sound quality, at least better than what you would have done without doing this particular course or without doing this particular module. So, hopefully, you have gained some knowledge to start with an auditorium design. So, here are some of the references for the particularly for the Sydney Opera House. You can see or browse through the references given over here, and you can always visit the Wikipedia to get more of visuals that can help you in creating or developing the sense or sense how you should treat your insight. With this, I finish this module.